Welcome. In this example video, we're going to go over the energy balance of a condenser. So we're going to do energy balances for a number of different kinds of equipment. Hopefully this gives you a little idea of how we would think about a condenser. So a condenser, what's happening in this piece of equipment is we have a stream coming in. This is steam. And it's coming in at 800 kilopascals kPa. It's coming in at a temperature of 400 degrees Celsius, and it's entering at a flow rate of 0.1 kilograms per second. So that is the m dot, right? The dot meaning a rate, m meaning mass. So the dot means a per second. And what we know about the outlet, we know that the outlet pressure is the same 800 kilopascals. Right, I'll write just a note. This is typical for condensers, if I could spell. Or boilers. Right, a condenser or a boiler is something where you're either adding heat or taking heat away. So typically we don't have large pressure changes, we have temperature changes. And it's happening, we know something about the amount of heat that's being removed. We'll call that Q dot condenser. So this would be what we call the heat duty, and that's 200 kilowatts. So this would be a 200 kilowatt condenser. Okay, so we know something about the inlet, we know something about the outlet, and we know something about the performance of this piece of equipment. And what our question is over here is determine the outlet state. So what's actually coming out here at 2? We know the pressure, but we don't know anything else. So we're going to go through step by step. First, we're going to do a mass balance. Right, so this is the sum of the mass flow rates exiting minus the sum of the mass flow rates coming in must be equal to 0. We only have one inlet and one outlet, so our mass balance is rather easy. M1 equals M2, so M1 equals M dot 2, and then we'll just call that M dot because it's the same in the inlet and the outlet. So there, we've done our mass balance. It's good though to make sure we go through some of these things step by step. Starting from the initial equations, because as things get more complicated, it will be, sometimes we'll actually have to go through and do a more sophisticated mass balance. Okay, but this one's fairly easy. The energy balance, we can always start with the general energy balance here, and then we're going to go through and simplify. So let's go through and simplify. I'm not going to write out all of these steps in detail like we did for the last example problem. I'll go through and talk through them, but you might want to take note of some of the language that I'm using and the assumption, the reasoning behind crossing some of these terms out. And that's the important thing, really. Like, right, we're going to go through and we're going to cross out terms, but we have to think about why we can cross those out. So the first term here, delta H. Delta H is the thermal energy of matter. So we have our piece of equipment here. Delta H is saying we have stuff going across the boundaries of our control volume. Right? If I were to draw a control volume, it might look something like this. I'll just label that as our CV. So we have stuff crossing over the control volume boundaries. So that's carrying with it some amount of thermal energy. So in general, we can't neglect delta H. Next, kinetic energy, delta EK. So this is asking, is there a significant difference in the kinetic energy of the stuff entering versus the stuff exiting? Kinetic energy, you have to start thinking velocities. Is there a big difference in the velocity of the matter entering or exiting? Typically for this kind of a system, it's designed so that there's not. Typically you design it so that the velocities are relatively low, so there would be changes. But that's changing from one low velocity to another low velocity, which means that typically the changes in kinetic energy are small. Same thing with potential energy. There probably are some potential energy changes. How I have it drawn here, there would be. Right, there would be a delta Z. But that's relatively small, certainly compared to the other energies in the system. And that's really what we're looking at. We're looking, is it small or large relative to the other energies that we're dealing with? Typically for a condenser like this, those are both fairly small. The next one is heat. Is heat crossing the control volume boundaries, or is the system insulated from the environment? Is heat going in and out? In this case, obviously, we have heat coming out. We have a condenser duty of 200 kilowatts. So Q stays. The last one is work. And that's asking, do we have any moving parts? Do we have any mechanical work being put into the system or being taken out? Is there like a spinning thing? Is there a mixer? Is there something that's turning, something mechanical, a moving part that's going to be either supplying mechanical energy or taking some of that mechanical energy out? And again, in this case, that would be equal to 0. So we have gone from 5 terms down to just 2. So our new energy balance is delta H dot equals Q. But we're not there yet. Okay, so we've simplified our energy balance, but we have to actually get it in a form that we can start plugging in things and looking up things in steam tables and actually figuring out the problem. And this is true of all of the left-hand side of the equation here. The delta is always talking about out minus in. So we could write this as, right, we only have one outlet and one inlet, but we could write, if we had more outlets, we could write all of those, provided we numbered them correctly. In this case, we just have one, out minus in equals Q. Right? Q and W don't have an out and an in because it's not talking about, it's not energy that's carried with the matter, it's energy kind of either going in or out at the boundaries of the control volume. So we don't talk about like Q out and Q in. We just talk about Q. Same thing for W. For work, we don't talk about work like work 1 and work 2, I guess would be a better way to say it. We just talk about work. All right, so this is what we have right now, H2 minus H1 dot in both cases equals Q dot. We can split this up a little bit more, right? Capital H2 is the total enthalpy flow out. So that's an extrinsic property. It depends on the amount of stuff that's flowing out, the mass, and it is a rate, right? That's what the dot means. So it's going to have sorry. The way that we can break that down, right, we want to get it into a term that we could actually look up in our tables. We could write it this way. Equals the mass flow rate times the specific enthalpy, right? This is mass flow rate, and this is the specific enthalpy. The specific enthalpy is what we're actually going to be looking up in our tables, right? That's the intrinsic property that depends on the state of the matter, whereas capital H is the extrinsic property. And sorry about some of the confusing language here, but capital H is the extrinsic property, which depends on how much we actually have. All right, so let's rewrite things a little bit. So we have now m dot H2 minus m dot H1 equals Q. Again, this is our energy balance, and then we can simplify this a little bit more because both have an m dot H2 minus H1 equals Q dot. So I'll just make a note here. We could look at specific heat transfer, and in some cases we will. Specific heat transfer would be Q dot. So capital Q would be equal to m dot little q. Right, this is the typical thing that we're going to see. The capital is equal to mass times the lowercase. If it has a dot, then the mass has a dot. But this isn't super helpful for us in this problem because we actually are just given what Q dot is, right? If we scroll up to the top, we're given a Q dot up here of 200 kilowatts. Okay, so let's start plugging in some numbers. So we have m dot H2 minus H1 equals Q dot of our condenser. M dot was 0.1 kilograms per second. This is H2 minus H1. And that equals Q of our condenser, which was 200 kilowatts. You write a little bit better W, kilowatts. So we can divide both sides, right? This is also kilojoules per second. So let's rewrite things. So this was now 200 kilojoules per second. That's a bad K. Kilojoules per second divided by 0.1 kilograms per second equals H2 minus H1. So the seconds will cancel out, and we get that H2 minus H1 is equal to 2,000 kilojoules per kilogram. Okay, so that's the change in enthalpy we have from the outlet minus the inlet. So we're going to be having a change there of 2,000 kilojoules per kilogram. What's going to happen? I should note this now. So something that's challenging about some of these, and we talked about this a little bit before, is the sign. Right, whether we have a positive or a negative, especially for Q and for W. right? So the sign convention that we have is from a steam engine. So in a steam engine, you put heat in and you get work out. So we consider both of those positive. So putting heat in is positive, getting work out is positive. In this case, in the condenser, we're actually taking heat out, so that would be a negative value. So I didn't put that in, so this should be a negative. Then this would be a negative here, and this is a negative there. Right, part of that gives me just an opportunity to talk about the sign and make sure that we have the sign correct. But you're always thinking the sign convention that you're using is a steam engine, where we would put heat in and get work out. In this case, we're taking heat out, so that means it's a negative. It's backwards to how a steam engine works. Right, steam engines, the birthplace of thermodynamics. So we're going to use that as our sign convention here. All right. So what we're trying to find is H2. We can look up H1. Right, and that's going to be, H1 is at 800 kilopascals and 400 degrees Celsius. So we can look up in our table, again, just as a practice. I'm not going to do it here. I'm just going to write down the answer. This H1 is 3,267.07 kilojoules per kilogram. So look that up. Make sure that you get the same answer that I did. Once we look that up, then we can find H2 directly, right? It's going to be H1 minus 2,000. So H2 is equal to now 1,267.07 kilojoules per kilogram. And then to look up what's actually coming out, we can look up in our tables the state where we have P2 equals 800 kilopascals and H2 is equal to 1267.07 kilojoules per kilogram. So we're trying to find those two values in our table. And what we find is that occurs at a vapor-liquid mixture. And we can tell that because the specific enthalpy of the fluid is 721.10 kilojoules per kilogram, and Hg is equal to 2,749.14 kilojoules per kilogram. And our value, 1267.07, is between those two values. So if we were less than 721, that would be a normal liquid. And if we were more than 2749, that would be a normal gas. Right, our first one, we started with a normal gas. Steam as a gas at 3267 up here. We're removing heat, and we've now turned some of that into liquid. It's not all liquid. We're not down to 721, but some of it has been turned into a liquid. So we're a vapor-liquid mixture at 800 kilopascal We know that we're a mixture because we're between these two values of the enthalpy. Now we can determine the quality. By this equation here, plus XHFG. So we're going to use the same equation that we used before. Here, we can actually plug in numbers for 1267.07 kilojoules per kilogram, and that will equal 721.10 kilojoules per kilogram, plus the quality, now times HFG, which is 2048, right? The difference between those two values, 2048.04 kilojoules per kilogram. And if we do the algebra there, we get a quality of 0.267. So what that's saying, right, our outlet state would be 800 kPa, and a quality of 0.267. Right, about 27% of our outlet stream is still vapor phase, so 73% is liquid. So we've condensed most of it, but not all of it. Hopefully this gives you some practice thinking about how we can solve these problems. As I said, figuring out how to simplify the energy balance is one of the biggest steps. And also just kind of a practical step, figuring out how to look up states from the steam tables, especially when you have stuff like this, where you have a pressure and an enthalpy. And eventually we'll get to like a pressure and an entropy, or a temperature and an entropy, and right, any combination, right, as long as we have two unique or two independent, can look up with two independent properties. And hopefully you can follow from this section here. I'll try not to have too many things. From this section here, how I could figure out that we had a vapor-liquid mixture instead of just a normal vapor or a normal liquid or a saturated vapor, saturated liquid. Figure out where I should be looking for my values in the tables. So with that, we'll wrap up this example on our condenser.